Hello everyone. In this lecture, I am going to discuss about some of the numerical problem related to magnetic circuit and transformer also. That will discuss very fundamental concept how to find the equivalent reluctance of a magnetic circuit, and based on that you can apply the Ohm's law for magnetic circuit, and then whatever the data asking question you will be able to solve it. So let us start first with a very simple example. The book is Nagrath book. I have taken this problem from the Nagrath book. And this problem says that it shows a rectangular magnetic core with an air gap. Find the exciting current needed to establish a flux density Bg. This is the air gap, and we have to maintain 1.2 Tesla air gap. Flux density given number of turn means this number of turn is given as 400, and this core, this magnetic material relative permeability is given as mu r equal to 4000, and it is saying that this is for iron. The magnetic core is made up of iron, and here number of turns are placed. So we are asked to find the value of current needed to establish a flux density in this air gap. This is the air gap. We have to find out the value of current. What is the value of current? This current we have to find out, so that the flux density in air gap becomes 1.2 Tesla. So we have to find the value of I. What is the value of I? So first of all, we can see here. So we can replace this number of turn. That is number of turn multiplied by current is called MMF. Number of turn multiplied by current is called MMF. And MMF is, I'm just drawing its equivalent electrical circuit. So here we can see that there is a magnetic core, and the reluctance of the core is represented by, this is called reluctance of the core. And then again there is a reluctance of the air gap, and here reluctance of the gap, and both are connected in series with an MMF of n into I. This is represented by this diagram, and flux will be flowing here. So this same circuit is also represented like a magnetic circuit. In electric circuit, EMF is here, current is here, resistance is here. But in case of magnetic circuit, MMF will be there, flux will be there, and reluctance will be there. Reluctance of the core is there, and reluctance of the gap is there. So we have to find out these value, reluctance of core and reluctance of gap. Then we will be able to find out the value of the current I needed to produce 1.2 Tesla flux density in the air gap. Here we can see very easily that this is given here, the dimension of the area of cross section of the core. Cross section means 2 centimeter is 4 centimeter is this side, and 4 centimeter is inside. So its area is 4 by 4 centimeter square, and the length of the air gap is 2 mm. So length of air, reluctance, first of all we should understand what is reluctance. 1 by mu naught mu r into L by A. This mu naught is the permeability of free space, and this is the relative permeability. So for the calculation of core, we need to find out how much length the flux is traveling in the core. This is the flux traveling from here, then coming here, and like this going this side. So we have to find the length of the core, but we have to keep in mind that this length from here to here is not a core, this is the air gap. So this whole length we have to calculate, and we have to subtract this length. Then we will get the length for the core in which flux is going. This is the length. You can see here, this is the length in which the flux is going for the core, means magnetic material. So first of all, we have to find length of the core. This is length of the core. We see, this is length of the core. I take this different color so that we can differentiate it. You see here, this length, then this length. So this length, this whole length is 16 centimeter, and 4 centimeter is from here to here. So 2 centimeter will be from here to here, and also 2 centimeter from here to here. So we have to subtract from 16 centimeter 4 centimeter, so that we can get this length. This length will be 16 minus, this length will be 16 minus 4, and same length will be here also, 16 minus 4 centimeter. Then again we have to calculate this length. So how much you can judge by yourself how much this length could be. So here also again 2 centimeter is from here to here, and 2 centimeter from here to here, and total length is 20 centimeter. So we have to subtract 4 centimeter. So 4 centimeter minus, we have to subtract. So 20 minus 4 centimeter, it will be 16 centimeter. Here it will be also from here to here, it is also 16 centimeter. But the difference is that air gap, we have also to subtract the length for air gap. So from here to here, I am writing this length like this. So it will be 20 minus 4 minus, this is in mm, so we have to convert in centimeter, so it will be 0.2 centimeter. So ultimately we have to add all this length to get the length of the core. Means 20 minus 4 plus 20 minus 4 minus 0.2, this length plus this length is 16 minus 4 plus 16 minus 4, means 2 into 16 minus 4. So after solving this, you will get the length of the core, which is equal to how much? Which is equal to 55.8 centimeter. It will come 55.8 centimeter. So now length of the core is known. So we can very easily find the reluctance of the core. So how can you find the reluctance of the core? So let us see. So reluctance of the core will be equal to 1 by mu naught. Mu naught is 4 pi into 10 to the power minus 7 into mu r. Relative permeability of this core is given in the question. It is 4000, and into length of the core. This length of the core is 55.8 into 10 to the power minus 2 meter. It is in centimeter, we are converting into meter, and then divided by area of cross section, 4 into 4 centimeter square, so 10 to the power minus 4 meter square. So now you use calculator and you can solve it. So we will get its value. Reluctance of the core is 0.694 into 10 to the power 5 ampere turn per Weber. This is the one part. Length reluctance of the core is calculated. Now we have to find out the reluctance of the air gap. How much is the reluctance of the air gap? So first of all, I take a different color. So reluctance of the air gap, reluctance of the gap will be equal to 1 by mu naught, and for air gap mu r will be how much? 1. For air, relative permeability is 1, and the length of the gap divided by area of cross section. So how much we will get its value? 1 by 4 pi into 10 to the power minus 7. This is the value of mu, and into 1 is the mu r, and into length of the gap is how much? 0.2 centimeter. So 0.2 into 10 to the power minus 2 divided by area of cross section is again same, this value. 4 multiplied by 4 into 10 to the power minus 4 meter square. So we need to solve it, and we will get its value, which is equal to how much? You can solve it by yourself also. Otherwise, I am telling you its value is how much its value? You can solve it. Its value is coming 9.95 into 10 to the power 5. 9.95 into 10 to the power 5. So this value is coming 9.95 into 10 to the power 5 ampere turn per Weber. So this is the value of the reluctance of the gap. So one thing I'm telling you here, a very interesting thing, you see reluctance of the core is small. Reluctance of the core, I'm taking different color to show its effectiveness. So here you see the reluctance of the gap is this much, and reluctance of the core is how much? Reluctance of the core is here. You can see it is reluctance of the core is this much. So you can see which value is higher. Definitely this value is higher. So we can say that reluctance of the air gap is very, very high as compared to the reluctance of the core magnetic material. So let us see now how we can calculate further. So we have two values, reluctance of the core and reluctance of the gap. And you see this flux is going in the air gap and same flux is going in the core also. So these two reluctances will be in series. So these reluctances are connected in series and MMF is represented like this. And so this is the reluctance of the gap and this is reluctance of the core and this is the MMF, which is equal to number of turn multiplied by the current, which is equal to MMF equal to number of turn multiplied by the current. And here it is phi. So from Ohm's law, we can say directly that number of turn multiplied by current MMF is equal to phi multiplied by the total reluctance of the core and reluctance of the gap. So this is called a series connected and this is simply equal to Ohm's law, V equal to I into R. This I is replaced by phi. So now this here, but everything is known. Here we have to calculate the value of phi first. So here flux density in the air gap is given. So flux density air gap is given. So we need to find first of all the value of flux in the air gap. How much flux is flowing in the air gap? So let us clear some space here. So now we need to find out the flux. So B equal to B in air gap is given. B equal to flux divided by area. So phi will be equal to B into area. And B is given as 1.2 and area is given as 4 into 4 into 10 to the power minus 4. So this flux, we will get flux here. So our flux is known. So we can put the value here flux and reluctance, both reluctance is known. And here in MMF, number of turn multiplied by current. So number of turn is known. So we can find here how much current is flowing. So let us make some space more here to calculate these values. So let's take this, what we can say that this value I'm going to. So let us see. So how can we find out this value? So flux, we have flux means 1.2 into 4 into 4 into 10 to the power minus 4. Weber is known. So in this equation, now we are using this equation. So MMF is number of turn multiplied by current, this N into I. And N is given in the question, which is equal to 400 multiplied by current I, which is equal to phi multiplied by current, which is multiplied by phi. Phi is equal to this much, 1.2 into 4 into 4 into 10 to the power minus 4 multiplied by. And we have again multiplied. So we have to add these two values to multiply. So which value you have to add? Reluctance of the core and reluctance of the magnetic material we have to multiply. Okay. So let us see. We are just putting this value here. So how we can get this value? Reluctance of the core is how much? This is reluctance of the core and reluctance of the gap. We have to add these two values, 0.694 into 10 to the power 5 plus 9.95 into 10 to the power 5. So here see everything is known. So just solve it and you will get the value of current I, which is equal to how much? Tell me the value of I. How much I is coming? So I is coming 5.1. So after solving this, you will get the value of 5.11. This is very interesting problem. Means here the flux is going, and a design problem means here flux we need flux density in air gap 1.2 Tesla. So how much current you need to supply here in this term? So you can say 5.1. If you give 5.11 current here, you will get here 1.2 Tesla flux. So next problem I am going to solve. So this is another problem based on the transformer. Again, it is very interesting problem, and we need to solve it. Very fundamental concept is the question is 200 kVA, 11,000 by 415 volt, 50 hertz single phase transformer has 80 turn on the secondary. Calculate the approximate value of primary turn, the full load secondary current and approximate value of primary current, maximum core flux, the secondary impedance which would fully load the transformer as its value as seen on the primary side. So these four values we have to solve. So this is transformer. Just I'm drawing the diagram for the transformer. It is like this. So this is the transformer, and it is like this. So here transformer primary is here. This primary induced voltage is, this is given as 11,000 volt, and secondary side voltage is here, induced voltage is 415 volt. So number of turn on single phase transformer, 80 turns on secondary. This number of turn, this is the N2, which is equal to 80. So we have to find the value of N1. So very simply, you must remember the relation V1 by V2 equal to N1 by N2 equal to I2 by I1. This is a very fundamental relation of the transformer, and you must keep in mind this V1 is also E1 and this V2 is also E2. Actually E2 and E2 is replaced by V2 and E1 is replaced by V1 for an ideal transformer. But for practical transformer, its value is slightly different, but for calculation point of view, we are assuming that V1 equal to E1 and V2 equal to E2. So now let us see how to use this formula just to find out the value of N2. So you need to use this formula. So just very simple, you apply here V1 by V2. V1 is here given as 11,000, and this is 11,000 divided by V2 is 415 divided by N1. N1 is not known, we have to find, and N2 is given as 80. So we are going to calculate it, and it's N1 will be coming here. It is equal to 210.48. So number of turn will not be in fraction. So N1, we take N1 as N1 2120. This is the primary number of turn. Now we need to find out the secondary number of turn, already given here, not to find. So now second part, what we have to find? In second part, we have to find out the value of current, full load current and approximate value of primary current. Full load current means secondary current we have to find. So transformer rating is also given as, for part B, transformer rating is how much? 200 kVA. So this 200 kVA is V2 into I2, which is also equal to V1 into I1. So here it is given 200 into 1000, kilo is removed, and V2 is given how much? 415 into I2. So just solve it, we will get it the value of I2. So I2 is coming here 481.9, 481.9 ampere. So similarly, we can also solve this relation. This value, this is also equal to V1 and I1. So you can also use the same relation, 2000 into 1000, 200 into 1000. V1 is how much? V1 is 11,000 volt into I1. So just by solving this, we will get the value of I1, which is equal to 18.19 ampere. So we can find the value of, we have solved the value of V1, V2, I1, I2. Now the third part is maximum core flux density. This is also very interesting, maximum core flux density. So how can you find the maximum core flux density? The primary current value is approximate because we have taken the transformer to be ideal. Now for the calculation of what we have to calculate, now we have to calculate the maximum core flux density. So for calculation of maximum core flux density, we have to use this relation E1 equal to 4.445 number of turn into frequency. So here see everything is given. This primary induced voltage is how much? It is 11,000 voltage, 4.44 into flux into number of turn is how much in the primary side, already calculated, 2120 into frequency is 50. Everything is given. So this is the maximum flux. You can solve it by using your calculator. So now third part is, last part is, that is D part, which is we have to find out the impedance from the secondary side and also impedance in the primary side. So we can find very easily impedance in the secondary as well as impedance in the primary side. So this one problem is showing everything in the question. So first we find the secondary impedance. So Z2 secondary impedance will be equal to V2 by I2. V2 is calculated. V2 is how much? 415 volt it is given. And I2 is how much? Secondary current here calculated 481.9. So secondary impedance, if you divide this 2, you will get the secondary impedance as 0.861. This is secondary impedance. Now in question it is also asked, transfer this secondary impedance to the primary side. So it is called Z2 dash, which is the secondary impedance referred to primary. So it is equal to A square into Z2, and A square is number of turn ratio, N1 by N2 square into Z2. So N1 by N2 is how much? It is V1 by V2. In fact, V1 is 11,000 divided by V2 is 415 square into 0.861. So just solve it, you will get the value of secondary impedance referred to the primary side, and which is coming approximately 60460. So okay, thank you. Next lecture we will see another problem.